Hola, everyone. Hello. Good morning, good afternoon, good evening, depending on which part of the world you're watching us from. Thanks a lot for joining in. Let me quickly go and check across platforms if you're live. Like every time, we do not want anyone to miss out on these learning opportunities. So I'm doing that. By the way, if you can see me, just feel free to comment. And I'd love to know that you are watching us. It's always great to see familiar faces who have been there with the community for a long period of time. So I'm just going and checking. Yeah, I get a notification we are live on a couple of platforms. Yes. You might also want to introduce which country you come from. That's an interesting thing that I saw a few folks do, which is really great. It helps people to get to know you better. So awesome. We are live. Great. Perfect. So let's get started in just a minute. Yeah. Last platform remaining. Yes, we are live across platforms. Perfect. So I'm so glad to see you all here. I'm one of the founding members of AI Planet. We've been known as DeFi so far, and my name is Mudit. I'm glad to welcome you all here in this particular live session where we'll be understanding more about text models and how they've evolved over a given period of time. Well, AI Planet, if you is a global community of data science. If you're new to it, so let me introduce AI Planet to you briefly. So, on our platform, you can access free learning resources by contributors like Mayank, who come forward to teach for free and educate the global data science community. We represent over 100,000 plus data scientists from 150 plus countries. That's in terms of numbers, but truly it's a community where we're trying to solve meaningful problems, and it's truly built by the community for the community. So, in this particular live session that we have right now, if you have any questions, please feel free to put them in the comment section. My team and I am having a close look at it. So, we would definitely try to take a note of it and pick them up towards the end. Now, talking about this particular session, we have Mayank with us, who's in the backstage. And unfortunately, this session started a bit late due to errors at our end, but he has been very patient, and you have been very patient. So let me do a quick intro of him. He's a research assistant professor at University of Southern California. He works in the Department of Industrial and Systems Engineering, and he's also a research team leader. Um, his research is into applied AI, and most of his applications revolve around complex networks and knowledge around graphs. His project is funded by a few notable organizations, and he's also an author with a few notable publications such as MIT Press Book. So without any further ado, let me bring him on the stage so that he can take us through the session, and it will be all his from there. Yeah. Hi, Mayank.
Hello, Art. Hi, everyone. So thank you for inviting me. It's delightful to meet this community and do ask lots of questions. We will go fairly quickly into a lot of material. So questions are really welcome. We enjoy that as educators and researchers. So my goal today is somewhat ambitious, so I hope to take you through what I refer to as a four generation overview of text. And so because we have very limited time, we will have to go very quickly, but I do hope to show you how our thinking has evolved on text, and also expose you to some tools, some terminology, so that you get more comfortable with text. That is my goal really for this session. So as Mudit already said, and I won't stop too long on this slide, we do work on a lot of projects in my group, and you can sort of see on the right-hand side some of the projects that we work on. So this ranges from applied AI projects, for example, in e-commerce, for crisis response, for understanding social networks and knowledge graphs, to social problems like addressing human trafficking. Financial fraud is another one. And more recently, we have also become very interested in problems of artificial general intelligence. So, we will refer a little bit to Chat GPT, which some of you might have heard about. That's one example of a system that is human-like almost in some of the things it can do with reservations. And so those are some problems and systems and models that we also look at. And one example is common sense reasoning. How do we build models that can actually have common sense? Very difficult problem, surprisingly. So this is just a range of things we work on. And to many of these problems, the one common element is text. To almost all of these, we require some kind of text analysis, deeper understanding of text. And so that's really what has inspired this presentation. So, let me begin first by, telling you about some of the problems in text analytics slash NLP, natural language processing. They are not one and the same. So NLP is a very important part of text analytics, but it's not the only field within text. So the two are not one and the same. That is the one thing I do want to say, although they are very related, very interrelated. So, I'm going to expose you to three problems right at the beginning to contextualize how we think about text. So one of them that you most likely heard about is very common. You might have seen it in undergrad classes. You might have seen it in Kaggle and other places, supervised learning, right? So this is something like spam classification, sentiment analysis. These are very classic problems in machine learning where, the idea is you get text data. Usually, some of it is training data, some of it is meant for testing. You train some machine learning algorithm, and then, hopefully you deploy it, you get new data, you get the results. So this is, standard machine learning pipeline. The only difference really is that the data is in text. And so you do have to do some feature engineering and some other things to make it work with the machine learning algorithm. So, given a piece of text, categorize it into one of several predefined categories. And in the more general case, it might be more than one category. So it might be a multi-set problem, etc. The second problem, which is slightly more advanced, but that we are actually more familiar with in everyday usage, is text representation. So this is where we want to encode the text, which could be words, sentences, etc., into some kind of data structure that captures the meaning and context of the text. So for those of you who are more familiar with this field, this might be vectors, it might be matrices. We'll see some options. But when you use the search engine, then the Google search engine, for example, is not really trying to categorize the text that you are putting in. It is instead trying to retrieve relevant information, like web pages that are going to be relevant to you, given your query, right? So the query is a text. The retrieved documents are also text. And in order to go from your query to the retrieved documents, the Google search engine needs to encode your text in some way so that it can work with it, can frame it as a retrieval problem. And another example is recommender systems, right? So if you don't have text, if you only have things like age, gender, previous behavior, these are easy to encode, right? Age is a number. Gender is a categorical variable. So, if it's male, female, you can represent the 0, 1, or if there are more, if there are more categories, you can represent it as more categories. But once you get text, how do we represent text in a mathematical data structure that we can then plug into a system? So this is also a very important problem. And the final one, historically the hardest, but very exciting progress in just the last 1 to 2 years, is text generation. So this is where you are given a prompt and then you want to generate new text usually. So, if I ask you a question, you give me an answer, and that is, kind of new. It's not, you're not retrieving a document, you're not retrieving a movie or something like that. You are generating new text. You might have to be creative, text summarization, poetry writing, essay writing. All of those are text generation problems. So, you can, and as you can see, these are not really disjoint problems. There's a lot of connection between them. So text encoding, for example, text representation might play a big role in supervised learning, similarly in text generation, etc. So these are related problems. I don't want you to think that they are all disjoint, but I think at a very high level, you can separate problems in text in one of these three buckets. So, as for many of these, you can apply NLP, but it's not just NLP. For example, information retrieval and recommender systems have some NLP in them, but it's a separate field. It's not, typically you will not see those things published in NLP conferences as much as, let's say, data mining, for example, right? In a lot of cases, you have to combine computer vision with the text. You have to combine categorical data like age, gender, etc., with the text. So it's not pure NLP. And so that's why I like to just call it text analysis, of which NLP is a part. So the goals really are, first of all, to enable you to think about these problems in a more systematic fashion. And the second goal that will be very important is to introduce you to practical paradigms that you can try out and apply. And one disclaimer is we are going to go very quickly, so I will focus primarily on examples and rely on high level intuition, but I will provide pointers along the way so that you can learn more about these. But it's there's a lot to learn, so I just want to make that very clear. And so don't worry if you come away a little bit dissatisfied that, okay, I would have liked to see more on this or that, because the truth is, by necessity, we have to be, I chose to be broad today rather than deep, so that you can learn more about the tools and paradigms that are more relevant to you. So with that, let me jump into 4 generations. And these 4 generations are useful for are not equally useful for all 3 problems that I just showed you. So supervised learning, encoding, text representation, and text generation. As we will see, each generation is actually useful for different sets of problems. So the first generation, which was really brought about, I would say, in the 1950s. So this is when computers were still in the punch card era, or even before. But already we were starting to see problems like information retrieval, like search come up. This is pre-internet, pre-consumer computers like desktops and laptops and so on. So this is very early, 50 to 60 years ago. And so these are frequency-based models. Now, before I go into what we mean by frequency-based models, some preliminaries here, which will seem obvious, but is something I always come back to, because it turns out there's a lot of nuance even in these preliminaries. So there are 3 words that I really hope you will remember. And these are dictionary words, so they are not very difficult to remember. So one of them is vocabulary. So vocabulary is a fixed set of words, which sometimes called terms. Then we have a document, which is a variable length list of words. And each word is assumed to be from the vocabulary. This is a simple definition. If something is not from the vocabulary, we say that the document contains out of vocabulary, or OOV words. But at first glance, you can assume that a document is a list. And I'm being very specific over here. I'm not trying to be vague over here. I really want you to think about it from a data structure standpoint. So vocabulary is a fixed set of words or terms. The word is usually a string. It's a finite string, right? So I didn't put that in because hopefully that's obvious. Document is a variable length, right? So you may not know the length in advance. The length is not fixed, but it's finite. You could assume it's finite. And the corpus is a set of documents. So set, list, set, all right? It's always useful to invoke this framework. So for example, right, if you're doing text generation, then we can say that the prompt, right, the input is a document. It's actually usually, I could say, okay, summarize what happened at Pearl Harbor. This is actually a document, right? It has words in it, and it's in an order. And we don't think of it as one big string. We think of it as a list of strings, right? So it's a document. So the input is a document. Same thing for a search engine. The input is a document. And the output, right, for text generation will be another document. And this document did not exist before, usually. So text generation is outputting a new document that didn't exist before. That's what the model has to do. On the other hand, information retrieval takes a document, which is your query, but is also taking a set of documents, a corpus, right? This is like all the documents on the web, let's say, right? Or if it's your inbox, then it's a set of emails, which is also a corpus. And then given a search term, the query, it will rank the documents in the corpus. It's not retrieving a new document. It's not creating a new document. It's creating a ranking over the documents in the corpus. So it's very important that you use these preliminaries, this framework, to think about how to what the problem is, right? It should not be vague in your mind. That is very important. It should not be vague. You must be very clear in your mind. What's the input, what's the output, and what's the model really doing? And then you can think about the how. How do we build such a model, right? Okay, so for frequency-based models, right, the insight, I'll give you the insight and then I'll show you some examples. So the first insight is that the frequency of a word in a document is a very important feature, right? So if a word occurs more often in the document, or even more obviously, if a word is present in a document, that is actually a very important feature. Now, this might seem obvious, right? But how do we operationalize this? Well, one way is that, let's take in Shakespeare's plays, right? As documents, the document could be in a column, and the vocabulary is in the rows, right? So each row is a word, and we put the full vocabulary in the row. So you get a matrix. And as you might imagine, the dimensionality of the matrix is the size of the vocabulary, which is a set, times the size of the corpus, which is also a set of the documents. And each element in the matrix, each cell in the matrix is in this simplest model is just a 1 or 0. It's not counting how many times, let's say, Antony occurs in Antony and Cleopatra. It's simply saying, does it occur in Antony and Cleopatra? If it occurs, give it a 1. If it doesn't occur, give it a 0. Now, you can immediately see that although it's limited, this is already solving some problems for you, at least in principle. First, it's giving you a vector, right? So now the document is getting converted to a vector of 1s and 0s. The word is also getting converted to a vector of 1s and 0s, and these vectors are fixed length. So for the document, right, it's not a stretch to imagine that you can actually apply this entire vector for Antony and Cleopatra into a text classification system, right? So if I want to know whether this is a tragedy or a comedy, right? So Shakespeare wrote both tragedies and comedies, and Antony and Cleopatra was a tragedy, Tempest was a comedy, right? And so on. So this is a binary text classification, right? Tragedy or comedy. And, I can imagine that, okay, I'll give some Shakespeare plays as training data. It's a vector of 1s and 0s. And, let's plug it into your favorite machine learning model, give it some labels, train the model. And, maybe it won't work very well. No one is saying that it will work very well, but, at least it's doable, right? You can create the vectors, plug it into the model, get a result, see whether it's working or not. The vector itself is also a representation, but you can't really solve text generation with this problem, right? As I said, most generations that you will see will actually not be able to solve that. It's only the very last generation, generation 4, where we make progress on text generation. But this will solve text representation and text classification to a first approximation, not the best model. The second insight is that, look, we should not just go for 1s and 0s, right? We should actually look at how many times the word occurs, right? So what is the frequency of the term, the number of occurrences of T and D, where T is the term, the word, and D is the document. But we should also look at what the frequency of the word is across the documents in the corpus. So one example is a word like this, right? This will likely occur, in here we are saying that this is a review classification problem, that, okay, this is a review of a movie. And what we want to know is the review good or bad, right? So again, that's a text classification. And if you do the incidence matrix, then you are simply, you would only do like 1, 0, right? But for, if this is your vocabulary, right? These are the only terms, let's say, in your vocabulary, very limited vocabulary. Then in this model, you can see that, for example, we are not just counting 1s and 0s, we are also counting how many times the word occurs. So in review 2, the word is occurring twice. Now, the IDF, which is the inverse document frequency, is usually, there are variants of it, but a very common definition is that the log of capital N divided by DF, where capital N is the number of documents in your corpus, and DF is the number of documents in which this term occurs. So if the word is, as you can see here, is occurring in all the 3 reviews, right? So DF, the number of documents in which the word if is occurring, is actually equal to N, right? So capital N is equal to 3 in this example. And DF for is, the document frequency for is also 3, right? So log of 3 by 3, which is log of 1, is going to give you 0. And that's what you see here. Now, what does this mean? If the word is occurring too many times in your corpus, then it's probably not that important. It's a common word, right? It's most likely a syntactic word or a common word. So we should weight the TF downwards. So when we compute the TF times the IDF, we get a trade-off. On the one hand, if the word occurs very often in a document, it's important for that document. But if the word occurs very often across the corpus, then it's not that important to begin with in an absolute sense. It's not very discriminative, right? It's not a discriminative feature. So you get this TF IDF vector, and you can see it's not a 0, 1 vector, it's a real valued vector. So already we are becoming more advanced. And this is what we call the bag of words model. It is still very widely in use. It is a very fast model. It is implemented in many systems. The Google search engine still uses, or till very recently was still using this model because of its speed, and it works very well. So even in this first generation, invented about 30, 40 years ago, this TF-IDF model, still widely in use, still the baseline, because of the powerful insights that it's trying to capture. Now, how can you try it out? The package I recommend is sklearn.featureextraction.txt, from which you can import the TF-IDF vectorizer. And if you go to the link, and you can also search for this on Google, sklearn TF-IDF, you'll see this link. It's very simple. You do have to do some work to get it to work, but hopefully the terms will now make sense. So there's a corpus. The corpus here is a long string. It is not actually a list of documents. This is the list of documents, but the document itself is not a list of words. It is represented as a string. But what happens is, then when you actually run the TF-IDF vectorizer, this takes as a parameter a way to segment the document into strings, into words. So that you can customize, because it depends on the language. It depends on whether you want to take punctuation into account, or do you just split on space, or do you also want to take punctuation, period, etc. So actually tokenizing the corpus into a variable length list of words, which is the proper definition of the document, is not actually a trivial problem, and you can use advanced NLP tools to do this as well. But typically there are some default tokenizers that will just allow you to split the long string into a variable length list of strings. So this is what you should try out. If you ever encounter a text problem, this is the very first thing you should try out. And this is always what we give in our classes homework. This is one of the most important homeworks, where you have to write a Jupyter notebook implementing an information retrieval system using TF-IDF. It's a graduate level homework usually, but if you work with text, this should be your first line of attack before you go into anything more advanced. Okay, second generation. Again, we're moving quickly, so stay with me. The second generation, and there is some argument whether this is really the second generation. One of my takeaways right towards the end will be that the generations are not, it's like our families, right? It's not that one generation has to finish before the second generation has to begin. Generations overlap, right? And in some families, one generation can begin before in another family, another generation begins, etc. So it's like that. Generations overlap, and so you should not get hung up again on, okay, they're all disjoint, and this generation came after this generation, or this generation is better than this generation. No, it's not like that. It's the analogy here is like a family generation. It's not that one comes strictly after the other and begins and ends strictly after the previous generation ends. It's not that one is better than the other. They are just different. They have their strengths and weaknesses. So the second generation, which is often the one that we teach first in our class, and this is naive-based. Hopefully many people have heard about this. Now more generally, the second generation is probabilistic graphical models. That's what I put here. And the easiest example of that is naive-based. So just like incidence matrix is the easiest example of a frequency-based model, the naive-based is the easiest example of a probabilistic graphical model. Now, for naive-based, best example is SPAM. So the idea here is that this is very good, by the way, for text classification. It's not so good for text representation. In fact, it's not clear at all that we can use this for text representation, nor is it good for text generation. So this is really very good for text classification. And many people use naive-based as the first line of attack. If you know that you have text classification, as the main problem that you're trying to solve, and you have a lot of label data. And you may not, in this case, right, you can kind of see here that we have these two examples. We want to classify if it's spam or not. And what we can do is that, again, not going into a lot of details here, but the idea is that the thing that you're trying to classify is which spam, not spam, is the top node. And these are probabilities. So the probability that a given message, the marginal probability, the probability of a message being spam, given nothing else, if I don't tell you what's in the message, right? So that's the marginal probability. The probability that the message is equal to spam is 0.6 and not spam is 0.4, based on our data. We learned this from training data. But then we have these conditional probabilities that given the message is spam, what is the probability that it contains the word million? And according to this, right, the probability that the word contains million given spam is 0.3. Now, of course, the probability that it does not contain million given spam would be 0.7, right? So that's why we are not putting it here, if you remember your probabilities. And the probability that the word contains million, given that it's not spam, the message contains million, given that it's not spam, is 0.1. And so similarly, the probability that the message does not contain million, given that it's not spam, would be 0.9. Now, this might make your head spin a little bit, but hopefully you can sort of see here the overall message is that now we are thinking about probabilities. That's the kind of takeaway from these kind of models, that they are trying to interpret the text, the content of the message, of the document, as probabilistic models. They want to frame it as probabilistic reasoning. And so, as you might imagine, if you get a new message for which you don't know if it's spam or not spam, what we would do, and we do an entire class on this, and hopefully you've taken a class on 9-base, but if not, then there are resources to help you learn. The idea would be you would be given the words, but you don't know if it's spam or not spam. So you would use these probabilities to figure out what is the probability of spam given the words that I'm observing in this message, and what's the probability that it's not spam given the words that I'm observing, and then whatever the higher probability is, you would return that as your prediction, but you can also return the probabilities as prediction. So this is very good for text classification. It works very well even today. It will get you, for most problems, if you have enough training data, this will get you all the way to 80-85% accuracy. Of course, if you want more than that, you have to use deep learning, which is the more advanced generation. But again, it's very quick. It can be trained with relatively small amounts of data, and you can also generalize. So you can go from naive-Bayes to what we call Bayesian networks, where you don't have to stop at one level. You can say that, okay, if you can derive values for what's the probability that you observe a million given the message is spam, what's the probability that you observe dollars given that the message contains million, and so on. And it turns out that the more, of course, it depends on how good your structure is of the, and how good your data is. But assuming you have a rich enough model, you would be able to capture, high level dependencies, and you would ultimately get a better prediction of whether it's spam or not spam. And another kind of graphical model is a topic model that I think some of you might have heard about. And this is a more advanced kind of graphical model. And the nice thing about this model is that it can be used for several things. So first, this is very good for learning text representation. It is not very good for text classification. So if you want to represent the document, in a low dimensional space, right? This historically used to be the first line of attack, because if you think about TF-IDF, right? TF-IDF and frequency-based model incidence matrix, the size of your vector, right? Let's say Antony and Cleopatra, the size of that column is equal to the size of your vocabulary, right? Because if you remember, each row in the matrix was a word in the vocabulary, right? So typically, if you have 5,000 words, 10,000 words in your vocabulary, which is usually the case, the English language has more than 1 million words in a vocabulary, and that's not counting words that are non-grammatical, right? Like words you would see on Twitter and hashtags and misspellings and so on. So vocabulary can be huge. And what that means is that the vector that you get from TF-IDF, from incidence matrix, is very sparse. For a given document, there would be many zeros, and machine learning does not like that, it turns out. So if you want a low dimensional, real valued vector, then typically you would use, the historical thing that was used for the topic model. And this is an advanced graphical model. We won't go into it, but uh, what you can also use this for is for getting these word clouds. So if you've seen these kind of word clouds where you send in the corpus and it gives you these word clouds, which tells you what are the different topics in the corpus, right? So this is telling you that, okay, in your corpus, you have documents about movies and television and entertainment. You have documents about computer and systems, documents about, democratic politics, election, and so on. This is obviously a very diverse corpus. Maybe it's a set of Wikipedia documents, for example, right? And very good for exploration. Now, where can you use this? Well, there's a Python package called GenSim, which is your friend. So again, you just have to do a pip install for GenSim. And once you do that, then it's very easy to use LDA model and to explore, right? So again, you don't need GPU or deep learning for initial exploration. You can just explore using LDA and get the word cloud, get the topic representation. However, right, this will not be as useful for supervised classification. If you want supervised classification like sentiment analysis, you will have to do a little bit more. There's an extra step where you have to train the model with labels, or you have to use a more advanced model. But this is, if you're just trying to use vanilla topic model, then this is your friend. Okay, so generation 3, text embeddings. Now, in terms of timeline, right, generation 1 was, as I was saying, kind of 50s, 60s era, 70s. In NLP in the 70s, already statistical models was starting to come into play. So, I would say that in the 90s, right? So, the TF-IDF plus, basic machine learning, some naive Bayes, etc., were all on their way, depending on which researchers or communities you talk to. But certainly in information retrieval, the by, I would say, the 1990s, 1980s, the TF-IDF was bag of words still dominant. The topic model, the naive Bayes, I would say, became very popular in the 90s and early 2000s, but topic models were really introduced in the 2000s. So the 2000s were really the era of the topic models, of LDA, and so on. And you will still see some papers on that, more advanced models, but 2000s were the era of topic models. Now, what I'm next covering, text embeddings, is the early to mid 2010s, right? So you can sort of see that the generation are accelerating, that for many decades, right? And even today, TF-IDF, frequency-based models, very popular. Even today in basic settings, naive Bayes and topic models are very popular, but it was only 20 years ago. So as far as, technology goes, science goes, it's still not, very old. It's not something that is 100 years old or 50 years old. It's not like calculus or 300 years old. It's 20 years old. So generation 2 is already only 20 years old, and this is only 10 years old. So all of this is fairly recent if you think about it in the long arc of history. Now, text embeddings, right, gets to the question that, okay, we can count the number of times words occur in a document. We can count, we can look at probabilities, we can do all of that. But, none of this is really telling us what the word means, right? Like what is, and also, we are not looking so much at the context of the word. So, for example, right, when we look at the word million in the naive Bayes, it's really not looking at what's occurring around the millions, right? It's not looking at what other words are occurring. So it's very, it's sort of encoding it, but indirectly. very indirectly. The text embeddings gets directly to the question that when we think about words and the meanings of words, the semantics of words, we must look at the context. So one example is, let's look at the word quark, right? If you look up the dictionary definition, it's a proper noun, so you won't really see a dictionary definition. But what you might see is, okay, it's a particle in physics. Um, it's also one of an important character in the Star Trek universe, and it's also a cheese, right? So there are three different meanings, and you don't need to know the dictionary meaning. If you just read this paragraph, which you should not try to do right now, but if you just eyeball this, it's kind of like really clear, just from the first few sentences, that, oh, this is a particle, this is a character, this is a cheese. Not only are they different meanings, but they are different types of things. That's how different they are. Like, one is a person, one is a physical entity like a particle, and the other one is a food entity, right? So it's they are not only different meanings, but different types, different concepts, right? So the context really matters when you are interpreting the meaning of the word. And so this insight has led to important advances in NLP in the early to mid 2010s. Now, the concept itself, that the meaning of a word really depends on its context, on the words around it, etc. This is not really, I would say, a new scientific observation. The scientific observation has been there for more than 50 years. So Firth's hypothesis, you shall know a word by the company it keeps, was documented, I believe, all the way back to the 1950s. And so in computational linguistics, in the study of language, it's very well known, in the study of semantics, study of computational linguistics, where they have looked at the issue of what gives a word its meaning, and also philosophy, etc. This concept was there, but the problem was that it's an abstract concept, right? It's a very theoretical concept. How do we actually use it for NLP and for text analysis? And so only in the early to mid 2010s was the idea proposed that let's use a neural network. And so one of the earliest ones was skip-gram model, which is the word-to-vec model. There are other word-to-vec models, continuous bag of words, etc. But here, right, the idea is you are trying to learn the vector for a word. So these are the x's, and you're looking at the context of the word, and you slide a window. You take the document, you slide a window of a certain length, right, over the entire document, and you look at the words around the target word, and then you get what's called the embedding of the word, and the neural network is giving you the embedding. And when we actually visualize the embedding in 2D space, and there are good tools for doing this, for taking a high dimensional embedding and visualizing it approximately in a 2D space, you can see that it's really interesting that what these embeddings capture very naturally are things like king is to man as queen is to woman, etc. So these are not given to the model. Just given a large corpus, the model can automatically capture these kind of relationships. And this was a really groundbreaking finding back in 2012 or 13 in a paper. And so neural networks plus data have really led to fruition of this hypothesis in practical applications. So it's also allows you to solve all kinds of other problems. So historically, the document embedding, the topic model, it turns out if you change this model a little bit, you can also get document embedding and so on. So there's been a lot of work on this. You can even train graph embeddings, and many people still do. It's the first line of attack. When you're if you want neural embedding, this is the first line of attack. Before you go into anything more complex, before you go into graph neural networks or even transformers, this is the first thing you should try, because it's very fast, it's very reliable, and there are many resources. So again, GenSim has a word-to-vec model along with the topic model, but Facebook Research has also released fast text in star space and GLOVE. GLOVE was from Stanford, but fast text and star space are from Facebook Research. And fast text, as the name suggests, really is very, very fast. So if you are in industry and you want a very fast, very reliable algorithm, fast text is your friend. So even I can tell you from my own experience, we work a lot with companies, and when I first talk to the engineers, they like to build things, right? As we all know from our developers, engineers, we love to build things. We want to pick up the latest and greatest, and we always feel like that will be the solution. And they try that, and it's tough, and transformers running slowly, difficult. You need a GPU. Sometimes they are unreliable. They will give you wrong answers with high confidence. And then we tell them, well, forget about that. Let's, why don't you just try this? It came out 6 years ago, and maybe you think it's old, right? But why don't you just try this, right? And see what happens. And they try it and they don't come back to the other model. That's what happens. So it's like saying, right, that, oh, you can try very advanced, fancy stuff, and a lot of times simple works just fine in real applications. All right. So again, hopefully, uh, this is giving you some pointers on what you can try. And by the way, FastText has a supervised version available. You can get document embeddings, you can get word embeddings, you can also train a supervised model. Start Space allows you to combine the word embedding with other modalities like images and graphs and so on, but it's not the best model, and it's a little bit iffy. I would still say that FastText is the classic, advanced Word2Vec, and was really built by the same person who invented Word2Vec. He went to Facebook research later on, and he developed FastText. And so, these came out of industrial labs and were meant to be very fast. So, these are things that you should try out. In fact, I would say that if TF, IDF, and knife base are not solving your problem or are not good fits, then before you try topic model, this is actually what you should try, FastText. And along with that, you can also try the topic model if you're installing GenSim. And once you do all of that, once you're familiar with that, then you should actually go to Generation 4. There's no denying that Generation 4 has really changed the way we think about NLP and text and so on. But in real applications, this should not be the first thing you try. This is very hyped up, and it's very good in research settings. It's very good for certain advanced problems, but this should not be the first thing you try. And if you do, then you will very quickly find that it may have been a mistake to try this first. So many people don't listen to me when I say this. So I hope you will listen to me, that don't try this first. Try Generation 1 and 3 first, and maybe 2. And Generation 4 should be, you can try it, but it should not be the first thing you try. Now, we've all heard about ChatGPT by now, right? I mean, you would really have to be living in a bubble even if you're not in computer science, even if you're not a developer. Hopefully you've heard about ChatGPT. The fear is very real. I don't want to say there's a correlation between Microsoft suddenly cutting 10,000 jobs and Google suddenly cutting 10,000 jobs. And then, tens of thousands of jobs are getting cut, at least over here, and not just over here in the US. But it's not just hype. And I'm not saying that ChatGPT is the reason why these jobs got cut, but certainly there is a very real sense in industry that we don't need so many developers. And that's the truth. There is a sense that, these programs can now write code on their own. And no, they're not all there. They can't just run our entire programming apparatus, right? But they are so good, and they will continue to get better. And developers are expensive. So, we can actually, we can train this system to be a developer. So let's have a developer train the system to be a developer. And, let's slowly automate the white collar work, as the Atlantic calls it. So these are all mainstream news outlets. They are not, far-flung science fiction news outlets. And so ChatGPT really is very impressive. So, for example, right here are some examples in case you haven't seen it. So, if you ask ChatGPT to explain the worst case time complexity of the bubble sort with Python code, I didn't show you the Python code example here, and this is from someone else, by the way. So all of this is on Twitter. This is generated by ChatGPT. So this is text generation on overdrive, the most difficult problem, and giving you very realistic issues. write a poem about the best way to break into a house. It's giving you a poem. This is not a full poem. There's much more. Um, ChatGPT has some impressive predecessors. Now, in my group, we work a lot with language models. So we have a number of papers that are being written right now. We've published papers before. So we are, that common sense project that I was talking about at the beginning is really big on language models. So it's an advanced project. The organization that is funding that project is DARPA, the Defense Advanced Research Projects Agency. To give you some background, DARPA was created right after the Russians launched Sputnik, right? So as you might imagine, here in the US, there was panic about that back in the 60s, that why weren't we the first? So DARPA was created actually for that. And if you heard the word moonshot, I would not be surprised if that word was invented, although I'm not sure about that, in that context, that, that they created DARPA to work on cutting edge 5, 10, 20-year down the line problems. And one of the problems we are looking at is how can we get machines to have common sense? And these language models, they are not there yet. They don't have what we might call common sense, but they're getting pretty darned close. And before ChatGPT, there was GPT-3, which you might also have heard about from OpenAI. Super impressive. Super, super duper impressive. I mean, no denying that. Has its flaws, super impressive. And there are other models coming up. The ChatGPT has really led to alarm bells in Google because it's coming from OpenAI, and Microsoft is saying that they will invest $10 billion. That's what I'm hearing in OpenAI. So Microsoft has a very close, connection to OpenAI and was one of the early funders and so on. So, Google is my sources, and not just my sources, but in the press, you just saw in the press articles that, Google and Facebook and some of these other companies, they're all here. You can see Facebook, you can see OpenAI, you can see NVIDIA, you can see Microsoft, you can see Google. So all the big tech, this is the thing we are paranoid about. They want the best LLMs, large language models, and there's exponential growth. And we can't train these models anymore on our own. The industry can train them, and it takes millions of dollars. And we're very fortunate that they release pre-trained versions. They release it as open, where you can pay to use the API and so on. But we don't know how long that will last and how much money will be needed to access these networks. So you can't train these networks on your own. That is the first thing I want you to know. It's very hard. That doesn't mean that you can't customize it. So the BERT model, for example, and Roberta and DistilBERT, these models are still very widely in use because you can customize it. You can fine-tune the models. What we do is we download the pre-trained model, which is big. We can't train the pre-trained model on our own usually. It still takes a lot of money and GPUs. But the pre-trained model, which has been trained on Wikipedia and on large amounts of text, is available. So you can download those models, and I'll show you the repository where you can do that. And then you can fine-tune it using a small amount of training data that is dependent on your application. So if you're doing supervised text classification, you can use a small amount of training data on top of the pre-trained model, and these models allow you to do that. And it's because of the way that these transformer-based neural networks work. So this is a fundamentally different kind of neural network that was published in 2017. And again, I'm not going to go through all these details. It's fairly advanced. You have to really read the paper to understand what this is about. And even before you read the paper, you need to know something about RNNs, recurrent neural networks, LSTMs. Those are preliminary. So you need to know something about deep learning and neural networks in general before you can fully understand this paper. And these are advanced concepts. You can try them out, but they are basically black boxes. And if you're trying to understand them, they're not that easy to understand. They require a lot of reading before you can really safely understand them without dumbing it down. Now, although rapidly evolving, and I only need a few minutes more and we can get to questions. Although rapidly evolving, there are already many good resources, and we are very fortunate in that. We should not take this for granted, because these companies can just, pull the plug. I mean, what's stopping them, right? They can pull the plug. They can say, you know what, whatever we release, go ahead, use those. We won't release anymore because it's a competitive advantage. They can do that. Whether they do that and whether they should do that, and whether it's in their own best interest to do that, is besides the point. That the point is they could do that. So I can only speak for what's happening now. Right now, we are very fortunate that you can try ChatGPT on the OpenAI website. You can, uh, you know, Hugging Face also is a private company, by the way, right? So it has been valued very high. It received private funding, another round of private funding very recently. It's a startup. And, it might go public and there might be pressure on it to not be as open. Later models are already becoming so big. For example, ChatGPT is so big that you can't really download the model, even if they allowed you to. You would not be able to download the model or run it that easily. You really have to access the model through an API. Um, and the future models will also be like that with trillions of parameters. You wouldn't be able to download the model. You have to access it through an API. So it kind of becomes like the search engine, right? It becomes like Google Map, or it becomes like the Google search engine, where you can have some free number of accesses, but then most likely you will have to pay for it, and that will limit how much you can use and what you can use it for. So we're in a golden era right now that we can actually use many of these things for free, and that the BERT and Roberta and some of the open models still work very well. But it's a rapidly evolving field. So even a year down the line, this could become outdated. Everything I'm telling you about this generation what I'm telling you now could become outdated, although transformers will not become outdated. Transformers are here to stay for a few more years before, another new generation, for all we know, would be here. We don't know yet. So wrap up. Um, Three takeaways. First takeaway, understanding text. And here the critical word is understanding, which includes words, sentences, and context, is a fundamental and still unsolved problem in AI. Now, when I say understanding, I don't mean applying. We can apply text analysis, we can do text analysis, we can apply NLP and so on without fully understanding the text. But, this we hit a wall when we do that, right? So there are some very deep problems like common sense reasoning, very human like problems of artificial general intelligence that require understanding. Unless we have understanding, we are not going to trust so called AGI. We will just think of it like a statistical bag of tricks, which, many people do think of language models that way, that it's a big statistical bag of tricks. It's, it's kind of like, another way to look at it is it's kind of like the Google search engine, but instead of, retrieving documents from this enormous corpus that is the web, that it is, kind of generating new text, but it's still kind of doing what the search engine was doing. It's really not understanding. It's kind of generating based on this huge amount of data. It's learning very advanced nonlinear statistics. There's a very big philosophical problem that, what do we mean by understanding? Maybe learning a big statistical model is understanding, right? So this is a philosophical issue. I won't go into it, but it's not yet fully solved. We still don't have what I would call deep, robust common sense and or other things in some of these models. Although we're getting there. We're getting there. These ChatGPT, etc., very impressive. Takeaway two, all four generations continue to be useful in different contexts and applications. If you want speed, right, TF-IDF, very difficult to beat. Bag of words, TF-IDF. Document search engines like Solr, like MongoDB, like Elasticsearch, still implement very efficient TF-IDF within them. So when you actually run a search query, they will retrieve very quickly using inverted indexes and so on, and they will be able to work very quickly. You will get extreme speed with those search engines if you're using a frequency-based model like TF-IDF. If you're trying to explore the data, right, then I would still say that the word2vec and topic model is kind of like a first shot, right, where if you have like good corpus, with thousands or several hundred documents that is very domain specific. I mean, a deep neural network will not be able to do very well with a few hundred documents unless you are using a pre-trained model and you train it on top of it, etc. So if you're looking for, I don't want to go for that level of complexity. I don't have time. I need a quick, good solution that I can do in 1 to 2 days, that will run in a Python script, that does not require a GPU, and that I know is reasonably reliable. Go for generations 2 and 3, or even generation 1, right? Word2vec. Gensem, topic models, those are your friends. So still continue to be useful. So the four generations are overlapping. So two and three are related, which is that the four generations are overlapping. There is no clear boundary between them. And some people would disagree that these are the four generations. So if you talk to an NLP person, they would not really look at TF, IDF, etc. as really a generation. And they might say that, okay, they might see it more as a neural network. That in the 80s we had the neural networks. That was when they were first applied, really. Or before that we had perceptron, but I don't really think of that as modern neural network. And so and then we had SVM and we had this and that. So it's different people think about generations differently, but in my view these are the four generations in an applied context that you really need to think about. So with that, I will stop here for Q&A. If one thing I do want to say is, I hope that you will I understand that not everything we could go into depth today, but hopefully there were enough pointers and enough guidance that you could learn more about the things that interest you. You can try it out, and do connect with me on LinkedIn. And if you're ever in the Southern California area, that's our office. So do pay us a visit and write to me and pay us a visit. We are very happy to hear from folks who are in the area and just want to get together for coffee or anything like that. So I'll stop here, and hopefully I haven't lost everyone in the meantime. But let me
No,
just stop
you
here. Yeah.
didn't. Well, thanks a lot for such an extensive presentation. I saw a few questions that were asked, and then you eventually answered them, which is interesting. There are a few questions that we can probably pick. So,
Sure.
okay. So one question that okay, this is a very specific question, but how are upcoming text models trying to handle the problem of polysemy and synonymy in the text classification tasks?
Yeah, so I would say that, I mean, even previous models, the word to vec, for example, was able to handle polysemy and synonymy, which are, by the way, these are um, uh, issues that arise when you're not allowed to. So the two issues that arise. One is that the same concept can be represented by different words, right? So that is synonymy. That is probably what people have heard about. But there are also problems like word sense disambiguation, where you have a word like quark or you have a word like bank that might mean different things in different context, right? So there's that problem. So if you look up word sense disambiguation on Google Scholar, or entity resolution, co-reference resolution, many different NLP problems. There were already, solutions, even going back to the topic model, the word to where people had proposed solutions to this. The upcoming text models, including the language models, they are just able to get much better accuracy. So these problems are not new problems in NLP, is what I'm trying to say. They were already being addressed 20, 30 years ago. What has happened is that as the new models come out, you get much better performance. So the accuracy goes up. So this is generally the case with these new generations, that the accuracy keeps going up, especially on the harder problems. But
Hmm.
even so, right? If you use simple word to vec, and again, it's how you use it is a more advanced topic. How do you actually use word to vec for WSZ and so on? And how do you use a knowledge graph or a knowledge network like WordNet, which is a very good resource for handling things like synonymy and polysemy, was invented in the early 90s. All of these, NLP people have solutions for this, and packages like Natural Language Toolkit, NLTK, Spacey is another one. You can use all of that for these problems. But if you really want the very best performance and you're willing to put in the work, and your domain is a hard one, but the text is challenging to work with, so this could be social media, for example, then yes, you do want to train a deep learning model. But it's not that you need deep learning to do it. You can use a 20-year-old solution to do it. Yeah. And
Okay.
yeah.
Okay, got it. There's an interesting question which has asked, and I would probably extend this further. Is what are any interpretability issues with the current or fourth gen text models? Maybe fourth gen is the better way to put it across now
Very
that.
good question. Yes. Very good question. So the question of interpretability is a cutting edge issue. So we don't have a clear answer to. Uh, so let me answer the question first. So yes, there are interpretability issues. So that's the answer to the question. Now, why does that happen? It's because these models are highly nonlinear, right? So let me give an example of something that is not nonlinear. So if you're using TF-IDF with let's say logistic regression, right? Um, the model tells you, okay, this is spam, this document is spam, and it will, if you ask why, right, then it will tell you, okay, because these words are present in your document and these words of high weight, and the high weight, right, in your regression, right, is a straight line, so there are weights on the word features, and your features are words, right? It's a frequency based model. So you can say, well, because these words are present and these words are associated with spam, right? So that's kind of a, you might argue that's interpretable. The moment you go to a generation 4 model, you can't really say, well, because this word was present, because it's highly nonlinear, right? So it's going through different layers. And so it's not enough to say, well, there was a weight on this word or there was a weight on that word. It's not enough anymore. It's things like, okay, this word was present in this context, and this context was present in this context, and these two contexts don't co occur. But we want the model to tell us that, right? But the model is not telling us that. So when we get an output, we are not sure why that output was there. Is it because of this word? Now, there's some solutions to this that were already being explored before, around 5-10 years before, because this problem came up even with Word2Vec. So some solutions that were explored were, well, let's say I have a document, I run it through the trained network, and then I get some output. Let's say spam, right? Let's stick with that. Well, if I remove a word from that document, this is just one example, it's not the only way, but you can see the logic in this. So if you remove a word and now you send a document with that removed word into the network, do you still get spam? Right? And if you remove the phrase, now you can imagine, you can't do this for every word, you can't do this for every phrase. That's, or if you and the other, you can replace a word with another word. That's, so there are like infinite number of things you can do to ask that question. So it's still not satisfactory, but it's kind of approximate way of asking that, okay, what led to the output. So that's one way of, or what was the deciding factor. Was there a deciding factor, right? Or if I remove something, would I still get that output? So there are, what this is showing you is there are some creative ways that you can try to deal with the problem, but it's not a very direct approach, right? You have to approach it indirectly. You can't directly ask the model, why did you give me this? So this is still an ongoing issue with the, and there's a saying that Chat GPT is very good at what we call informed BS. So I don't want to swear on the platform, but there's a saying that Chat GPT is very good at giving you informed BS. I just saw today that there was a post just before joining this call. I saw that an associate professor at the Wharton School at UPenn, right, one of the world's best business schools, actually is allowing his students to use Chat GPT for essays. And I think it's a very good thing that he's doing that. And one of the guidelines he's put in his syllabus is that Chat GPT, you should not, you are responsible for the accuracy of ChatGPT. So you can use ChatGPT to generate your essay. I have no problems with that. But you can't say that, oh, there's a wrong fact in here, or there's something wrong here, or this doesn't make sense, or the essay is not very coherent. And what can I do? ChatGPT gave me that. That's not an excuse. Use ChatGPT, fine. It will give you a first run, but what you get will depend on your prompt, right? So what your prompt is, so you should try different prompts. And then when you get the essays, it's your responsibility to read the essay, to make it more coherent, to modify it, and to check the facts by using external sources. So trust is an issue, right? Like, is this true? Is this not true? How do I find out? Do I have to consult an external source, right? And if I have to consult an external source, then what uses the model, right? So
Right.
these are all issues that are cutting edge. We don't have answers. But yes, there are interpretability issues. Yes, there are trust issues. Um, and they are leading to very interesting questions and research directions. Yeah.
Okay. Well, thanks. It's an interesting set of arguments that you've made. And yeah, I did not hear this earlier when you said it's, about the informed BS thing, which is interesting of putting it across. But yeah.
because it sounds believable,
Yeah,
right?
yeah, yeah,
That's the
yeah,
thing.
yeah,
What used to
absolutely.
happen before was that the earlier text generation models, which, as I said, really before ChatGPT and GPT-3, text generation was very bad. It could not, like, no one was even thinking about it really. It was so bad, could not be used in any real applications in its pure form. And because it was so bad, if the model performed poorly, or was giving you BS, you could really see that it was BS. It was kind of easy to see it. The text was incoherent, it didn't make sense, it was ungrammatical, sentences didn't flow together. So you had like obvious syntactic, grammatical, obvious ways of determining that no, I can't trust this, right? But now it looks very believable. So it sounds very believable. So it's really a wolf in sheep's clothing in a way, right? And you can't really figure out, is it a sheep in sheep's clothing or wolf in sheep's clothing? So you really need external mechanism to do that. And we still don't know a good way to do that, because we don't know which sentence is reliable, which sentence is not reliable. So maybe in the future, the model will be modified to actually give more insight into that, but it's not there yet. So I hope they will work on it, but it's not there yet. Yeah.
Okay, well, thanks. There was one more question around trade-offs between various models, but then you answered that towards the end. Um, there is there is one question which is quite interesting. Is like, uh, it's something based on what you said. Like transformers will be there for a few more years. Like, what are the next steps and potential advancements that would replace transformers? Why do you say it's for a few more
So I
years?
have two reasons for saying that. So one reason is that, I mean, just historically, right? And I could be very wrong on this. It's possible there will be nothing super new after Transformers for another 15, 20 years. It's possible, right? But the pace at which we're seeing this, right? We had the word to vec, which was a neural network, but it was shallower. It relied on a different intuition, which was the window, right? You slide a window over the text, and there are like three layers basically, and you could get a good embedding. Um, then we had, the RNNs and LSTMs were being applied at that time, but were not, all that competitive with Word2Vec. They would give good results, but were not super competitive, I would say, with Word2Vec for simple applications, for simple settings. And then Transformers came along and really took off. It took them a couple of years to take off. 2017, the first paper came out. By 2019, I would say that they were 2019, end of 2019, early 2020, they had become super mainstream. And now it's real time. So a model comes out, and then within a day or two, there's like press on it and so on. So it's picking up pace. I think the transformers will become bigger. So what will happen is they're already becoming bigger, and there's a lot of criticism for that reason, because they take a lot of energy to train. So the estimate is that to train a GPT-3 or Chat GPT, it took like what would take like 100,000 US homes in an entire year. That much amount of energy. That's why it costs $4 or $5 million, $6 million to train the model. Um, and so this will likely become even more expensive. And so climate change and all these things that are being talked about now is leading to pressure to make these models more efficient. There's also research showing that the models don't have to be that big. There are some interesting lines of research that are saying that the models can be smaller. The model can be much smaller and can still give competitive performance that is roughly equal to what the big model was giving. And so this is leading to the question of how big does the model need to be, and can we make the model much smaller and more energy efficient? So there's a lot of research happening on this. And so we may still have the transformer, or it leads to a new neural network because of those kinds of advances. So that's one thing that we have seen transformers come 5 years after Word2Vec, and now we have text generation transformers that are now mainstream. And so 5 years later, we could have a totally new neural network that is not like that is the next, that is not a transformer, but is also not like a complete jump. Like transformers do have a connection to LSTMs and RNNs. There are some common features between them, so there could still be common features. A second reason is that, so these are the practical reasons, they're getting bigger, and they could change because of sparsity, because they are required to be more sparse, and we might hit a wall. And then if you want the next innovation, then you have to do something different. So that's one reason. The second reason is that the deep learning pioneers, some of the deep learning pioneers, who incidentally were not really informed, they were not involved in transformers, I would say. So Jeff Hinton and so on, they were very involved in the CNNs, the convolution neural net. That's my understanding. that they had a big role to play in the original deep networks that came out in the early 2010s, especially in computer vision. But transformers were really a Google thing initially, and were not really. I mean, Hinton certainly I don't think was involved in the invention of the transformer, but Hinton is working on something called Hinton, and some of the original deep learning pioneers are working on new kinds of neural networks, and they have been very open about that. So there's a new kind of neural network called a capsule network that they are now trying to work on. There are DeepMind and some of the other big wigs in deep learning are trying to combine. But I don't know whether DeepMind specifically is trying to do this, but certainly in the community, there is talk of combining reinforcement learning with text in some way. This is something we have heard about a lot as well, and we might be exploring this in our own group. And so, if transformers and reinforcement learning together, it doesn't seem all that obvious. So maybe you need something new, right? To like a Q learning plus transformers could lead to a new kind of network, or it might just be So this is all speculative, but just looking at the horizon, there's there is work that is being worked on. There are things that are being worked on, concepts that are promising that are being worked on. They might just fall by the wayside, or one of them or one or more of them might lead to something that is very different. And given the amount of money that is being spent, I would not be surprised that the paranoia that something new hopefully will come out a few years later, but it's unpredictable. We don't know when it will be. It could be next year, it could be 10 years later. So, yeah.
Yeah, well, that's an interesting take, and well, with that, I think we are almost. There are a few more questions, but then we have overshot the time. So, I thank you very much, Mayank, again for being with us today, and I think it was a very extensive session. You also shared various, like you went beyond the presentation. You covered insights from the community, highlighting some very interesting aspects. So, I'm pretty sure this was a very insightful session, and given the way at which text models are progressing, this might as well become obsolete a year down the line, most likely. But I think, well, thanks a lot for being with us today, and giving the entire set of insights about four generations of the models as you classified them.
Yes, the models might become obsolete, but the fundamentals never become obsolete.
True.
So that's the thing you have to remember, that there's, as these models become more advanced, there's actually more focus on fundamentals. So the fundamentals will never go out of fashion. So if you really want to get into the field, learn the fundamentals, and you're in good shape. Yeah.
Okay, well, awesome. Thanks for that last recommendation. And with this, we'll wrap this up. And we thank you all for being with us at this point in time. We'll see you again next Saturday. Happy weekend, happy learning. Cheers.
All right. Bye bye.